everyone. My name is Yosuke, CEO of QuEL, which is a startup launched 2 years ago and developing qubit controllers. So today, I will share our product and achievement and also future plan. A qubit controller is a device to input and output microwave pulse for qubit control. And qubit controller is necessary for quantum computer development, but it is sometimes troublesome for researchers. One is because its cost. It is more than 50% of total hardware cost. And also maintenance and calibration. Typical quantum qubit controller is like this. So researchers need to connect everything with many cables, and it is very time-consuming for construct and also maintenance. So the scaling up is every time difficult for researchers and because of qubit controllers. That's why we developed our product called QuEL1. It is all-in-one, very easy to use. Researchers just use this one. They don't have to suffer from time-consuming calibration and maintenance. Of course, it satisfies their very high signal quality requirement, and also it is scalable. As you can see, researchers just put multiple QuEL1s in 90-inch racks like this to expand their system. And it is maintenance-free. It is less expensive than a competing product. Inside of QuEL1 is like this. We have FPGA in the middle to make a pulse form, and also we have LSIs like DSCs, mixers to make a microwave. And also, our technology is patent-backed. So mainly, synchronization, and so channel-to-channel isolation, and also computer architecture of itself is patent-backed. So this is an example of our environment with our QuEL1s. So you can see how to use multiple QuEL1s with qubit and refrigerator. In terms of our achievement, we have tight collaboration with RIKEN, which is the largest research institute in Japan. So several months ago, RIKEN began operation of 64-qubit superconducting quantum computer with our qubit controllers. You can see world-famous Professor Nakamura here, and so also our QuEL1s are on his back. He used 12 units of QuEL1s for controlling 64 qubits. And so we became a fifth group, a world fifth group after Google, IBM, etc., to achieve more than 50 superconducting qubits. And the unique thing about us is we are only one company among fifth groups, fifth research institute and companies to sell qubit controllers. So IBM and Google don't open their information about qubit controller, so they hide their know-how and technology. But we sell proven technology to outside. That makes ourselves very unique. And in terms of sales, we sold qubit controllers for over 130 qubits in total last year, and around $3 million revenue. And this year, we already have a purchase order and plan to double the revenue. And this timing is perfect for scale up. So we have proven technology for scaling up the number of qubit, and we can supply companies and the research institute who want to make their system bigger. So in the next year or next year, 1,000 qubit NISQ will come, and we can supply such size of qubit controller to companies and research institute. Sorry. In terms of market size, current market is small, mainly for R&D use. But as quantum computing becomes commercial, the size of qubit market of qubit controller will be bigger. And in the next several years, it will reach over $10 billion US, mainly for business use. We supply not only quantum control hardware, but also hardware management system and also software, including API, sample codes, so on and so forth. And so we can provide total solution for qubit control for users, mainly researchers now, but in the future, companies. So in terms of team, we have experienced members with diverse background from quantum information, FPGA, software, electronics. And for me personally, I'm a serial entrepreneur in electronics field and jumped into quantum market 2 years ago. And this is a future plan. Our concentration is increasing number of qubits. We plan to ready a small size qubit controller for over 1,000 qubits in next year. And also, we are planning to expand our coverage to other types of qubit, like trapped ion. And FTQC, in terms of FTQC, we have participated in Japan's national project called Moonshot, and collaborate with LSI and the supercomputer researchers to research on future quantum computer architecture. So if you are interested in our company and the product, please contact me. Thank you so much.
Let's give him a hand of applause. Thank you, Yosuke. Great presentation there. Okay, let's start the questions going. Please.
Thank you for your presentation. I want to know more about the market size. How many potential customers are there in the market, do you think?
Potential customers. So you mean the future market size?
Yeah, future market size. And
so currently, our major customers are researchers. So they research on quantum hardware. And after their research, how can I say, so finishes, so the quantum hardware will go to business use. And after quantum computers are become commercial, so probably data center of quantum computers are built all over the world, and some companies purchase on-premise quantum computers. And in that case, so I cannot imagine. So like 1,000 quantum computers will be sold in a year or something like that. So that will be a great market. So, but now, even now, so we can get so R&D. We can cover R&D cost from revenue. We are not venture back now, but the future market potential is really big.
Okay, thank you.
Okay, one last question.
You are tackling a very, very interesting or very important problem in the market. Yeah, so that's for sure. But I would like to better understand what you just explained, because your technology, you are currently focusing only on superconducting technology.
Yes.
And the big guys in that game are basically hiding their controlling technologies, right? So how do you think overcoming that hurdle or that challenge?
So your question is about so how to move to other types of qubit, right?
Yeah, you could either go into other technologies, or you need to partner with companies like
okay.
IBM.
I understand. So actually, controlling other types of qubit is not so different. So we can use our technology. We can use the same technology for some extent. So we need to change. How can I say? Like a microwave frequency for other types of qubit, but not so different. So I think we can develop some kind of electronics for other types of qubit, and but we can use the same architecture of like for making waveform, or so synchronizing multiple units, something like that. So we don't have to change much for controlling other types of qubit.